There are several other groups of formulas that we want to have a look at now. They come in various categories: power-reducing formulas, half-angle formulas, product-to-sum formulas, sum-to-product formulas. They're written in your textbook. We're not going to look at every one of them up here, and I invite you just to kind of go over them and use them as reference. Now, we're going to just consider a few problems involving these in just a moment, but they're useful in simplifying certain expressions and in solving equations, as we'll see. Now, understand, though, the purpose of having these formulas, which can also be thought of as identities, but power-reducing formulas. Now, that means that we have a sort of a higher power and we want to reduce the power involved in our trig function. Half-angle formulas, we use these just like the double-angle formulas. Product-to-sum. It's as though we have a product, we're looking at a product and we want to express this as a sum. Here, sum to product. We have the sum of two items, that is the sine of one angle plus the sine of another angle, and we want the product of a couple of items. And there's a particular purpose for going through and using formulas such as these. Well, let's take a few examples. Now, again, I want you to think about these formulas as reference and just look at them in the textbook. Look at where you can find them. Look at the examples that are in your textbook and how these are useful. And then just use the list as reference. Okay, for this one, for sine 165 degrees, let's say we want an exact value for this. So we try to use double angle or half angle ideas in simplifying sine of 165 degrees. With a little investigation, we find that if we double 165 degrees, it turns out to be 330 degrees. And 330 degrees is one of those handy angles that has a reference angle of 30 degrees. So we're going to use a half angle formula. And the one we're using involves sine, of course. So it's sine u over 2, you see, is equal to, and I'm just taking this right out of the list, you see, and fitting the pattern for this formula using this particular problem. And that's what this study is all about. So here's the pattern that we want to match, and we want to match the pattern using this particular problem. So we're writing 165 degrees as 330 degrees over 2. And now we can use this half angle formula for sine. And all we're doing now is, now notice that in the formula, in this expression, we have cosine u, and u is the value in this numerator. And so here, to use it in this specific problem, it's the cosine of 330 degrees. All right, and everything else is brought down just as we see it. And now it's just a matter of evaluation, and it's pretty easy. Cosine of 330 degrees, we have a reference angle of 30 degrees. It's in the fourth quadrant. Cosine is positive in the fourth quadrant. Turns out to be the square root of 3 over 2. So just filling in, it's a pretty simple matter to fill in and analyze that situation. And now it's a matter of algebraic cleanup. Now we see a complex fraction situation here, and I think the easiest way to deal with it is to just take the common denominator of all small fractions in both this big numerator and big denominator and multiply that common denominator times both the numerator and denominator. That is, here we're multiplying by 2 over 2. You see, when we multiply 2 times the 1 up here, we get 2. 2 times this fraction, the 2's go out, and we have the square root of 3. 2 times 2 is 4 in the denominator. Now we can think of applying the radical to the numerator and denominator separately. We can't resolve the situation in the numerator, but we can certainly resolve the situation in the denominator. The square root of 4 gives 2. Now let's talk about the sign pattern here. This plus or minus value is just in here to choose the one appropriate for your problem. That's the idea. And appropriate for our problem. Now, although we used, within this problem, we used an angle of 330 degrees. You see, that's not the one that we're trying to find the sine of. We're trying to find the sine of 330 degrees over 2. That is, the sine of 165 degrees. And an angle of 165 degrees falls into the second quadrant. And the sine of an angle in the second quadrant is negative. So we would be choosing then the negative value here. So it's the negative of that fraction. Here's a situation where we can use a formula to help us solve an equation. Now, we see this, when you first look at an equation like this, just analyze it kind of like this. We have two different ratios involved. All right, now, one thing that we want to do is rewrite in terms of one ratio only. All right, that's one thing. Also, we have this half angle idea over here, so we want to get rid of that if we can. Well, we can certainly do that rather easily by using the half angle formula. Now, we're applying it here with cosine squared x over 2. And remember that cosine squared x over 2 means the cosine of x over 2 all squared. So we're just thinking cosine x over 2, using the half angle formula for cosine, it's plus or minus 1 plus cosine x over 2. You see the x, this value is the numerator of that fraction. And that's all there is to it. So we apply the formula. Now this squaring operation here is outside of the parenthesis when we write it in this form. And then I'll take it one more step before we even look at the other side. But plus or minus, when we square, we get plus. And when we square the radical disappears. And so we have simply 1 plus cosine x over 2 here as this part of the problem, as this factor, and when we multiply times 2, the 2's go out. So we have 1 plus cosine x. Well, that's rather nice. And then we look at the two sides of the equation and we think, well, how can we rewrite this so that we're dealing with only one ratio? And we can do that pretty easily by taking the sine squared x and rewriting as 1 minus cosine squared x, using that primary Pythagorean identity. All right, and then we just resolve this situation. We're noticing here right away, though, that we have a quadratic situation, so that we're going to probably solve by factoring. At any rate, we have, let's see, minus 1 plus cosine squared x. And then I'm also moving these terms away from, just clearing them from the right side. So I'm subtracting 1 on both sides, and I'm subtracting cosine x on both sides to accomplish that. And now we just clean up here. I'm writing the term of highest degree first, and then the first degree term, which is minus cosine x. And then a really nice thing happens. 2 minus 1 is 1, and then 1 minus 1, they go out. So we have simply this. Factoring, we take out the common factor of cosine x. Take cosine x out of this term, we're left with cosine x. Cosine x out of this term leaves minus 1. And now off we go with analyzing these two factors. Once we're in a factored form, and that's what we're kind of driving at in all of these kinds of problems, but once we arrive at that factored form, we can then say, we'd like to know the value of x that will cause each of the factors to become 0. So we go like this. Now let me backtrack over here because I'm just about out of room at the bottom of the board there. So I have this factored form. I'm just repeating the bottom step here. And now I'd like to know the value of x that will cause cosine x to be equal to 0. And I didn't mention it before, but let's assume here that we're going through one period here from 0 to 2 pi, and let's not include the 2 pi. So the x that we're looking for here is between 0 and 2 pi, but not including the 2 pi. All right, now, and in a similar way, we just take this factor and set it equal to 0, take the other factor, set it equal to 0, and then deal with them as sort of like separate problems. Now, the cosine of what angle is equal to 0? Well, we imagine the cosine curve. So we think in terms of, well, let's see, the cosine curve. Now, cosine of what angle is equal to 0? Well, that would be the angle at these points. Now, we know this to be pi. This is pi over 2. This is 3 pi over 2. So x then needs to be pi over 2, or x is 3 pi over 2. Now, for the other one, it's a similar kind of analysis. It is that the cosine x equals 1. And now the cosine of what angle is equal to 1? Well, let's see. Again, we kind of look at the curve here, and we're seeing that we're at the top of the amplitude here at an x of 0. So x needs to be 0 for this to take place. It also occurs at 2 pi, but we're disallowing that value because we're kind of back where we start from, you see, in this complete cycle idea. So our three answers are pi over 2, 3 pi over 2, and an x of 0. Here's another equation we want to solve. Now, notice we have the sine of some angle here plus the sine of another angle here. And we'd like to create a situation where we have factors involved. If we can look at a factored form on one side of an equation, then we can set each factor equal to 0. So the idea is to try to take this sum of two items involving sign and rewrite as a product. Well, that's the idea of sum to product, you see. And so we're going to use this identity. It's the sine of one angle plus the sine of another angle is equal to this product. 2 times sine of and cosine of. And we just kind of follow our way through this. We have a guideline here. It's just a formula, so we're going to fill in. So we have, let's see, we're just applying this idea, this formula, to this expression. Now, and notice, it's the x and y are the 6x and 2x involved up here. So we just fill in for those. So it's 2 times sine of the sum of the two angles in the numerator. Well, it's 6x plus 2x, you see, over 2. That's why I have this here. And then for cosine, it's cosine of the difference of the two angles. Well, that's 6x minus 2x, you see, over 2. So 6x minus 2x over 2. And now it's just a matter of simplifying a bit. 6x and 2x, that's 8x over 2 is 4x. And now 6x minus 2x over 2, 6x minus 2x, that's 4x over 2 is 2x. So now we go into this idea of a factored form, and so we set each factor equal to 0. Now the 2 doesn't contribute anything to our list of solutions, but certainly the other two do. Sine 4x then is equal to 0, and we like the values of x that will cause this to be true. Same idea with cosine 2x. We set it equal to 0. We ask ourselves what values of x will cause that to be true. Now we do have to consider the notion that if we're thinking about x as lying between 0 and 2 pi, then we have to consider where 4x would lie in 2x in terms of the evaluation of each of these separately. So, well, let's see. If 4x, to consider 4x, we think, well, if we want x to lie between 0 and 2 pi, and notice that this is a strict inequality here, then I'll multiply in all parts by 4 to understand that my cycle here for this analysis is between 0 and 8 pi. You see, and for the other one, for the cosine of 2x, it's between 0 and 4 pi. All right, so we come back over here and we think about it like this. We think, well, the sine of some angle is equal to 0. And we then immediately go into the idea of the sine curve. All right, so we think this way. We think, well, the sine curve behaves like this. And we know this position to be pi. And here's 2 pi, and here's 0. Okay, so we have zeros for angles of 0, pi, and 2 pi. So 0, pi, and 2 pi make this true. But we have to extend this out several cycles. We have to extend it out to 8 pi. What we're noticing about the pattern, though, is that at the end of every pi length interval, we have another 0. So we have 0 and then pi. 2 pi, there'll be another one at 3 pi, 4 pi, 5 pi, and so on. So all the way out to 8 pi, but 8 pi is not included in this group of solutions. We said that we go up to, but not including the 8 pi. So we go up to 7 pi. And then it's a matter of saying, well, gee, if 4x, if the angle we're talking about here, you see, this is the angle whose sine is equal to 0, and we're finding those angles here, but it's 4x that we're finding. To find x, we need to divide through by 4, and dividing each of these by 4, we get various solutions to our equation. In a similar way, we analyze the situation for cosine 2x. Now, for the cosine curve, we think, well, for what values is this true? That cosine of the angle is equal to 0, and the angle happens to be 2x. So 2x takes on values of, and then we look at the cosine curve, and it turns out to be pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And, well, let me show it to you just to make sure we understand how that comes about. You see, we look at a cycle of the cosine curve, and here's the pi over 2 and 3 pi over 2. And then we go through 2 cycles of this. You see, it's pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, so that's the idea. Now that's 2x though. 2x takes on these values. So what would x take on? Well, take half on both sides. Half of pi over 2, pi over 4. Half of this, 3 pi over 4. Half of this, 5 pi over 4. You know, these are starting to look rather familiar. If you look at these items, they are all items that are contained in this big list of solutions over here. So it turns out that this then is the complete list of our solutions. Now, if you look at the pattern here in terms of common denominator, that'll help us here with what we're going to do next, which is to look at it on the graphing calculator. This can be thought of as 0 over 4. But this is pi over 4, this is 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. You see, all of these are just various values of pi over 4 for all of these. Now let's look at it and verify the idea on the calculator. The equation is in place, sine 6x plus sine 2x, and here are the window settings in case you're doing this along with me. The x minimum is set at -0.3 so that we can see the distinct x-intercept at 0. X max is 6.28, this is 2 pi. The scale, the x scale, has been set at this decimal. Now I entered this as pi over 4. Because we'd like to see increments of pi over 4 along the x-axis because that's where we're expecting the intercepts to fall. The y minimum is -2, y max of 2. And here comes the graph. 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi. The 8 pi over 4 doesn't count because that's nothing but 2 pi and that's not part of our domain. So these are the expected x-intercepts that we found earlier algebraically.